Okay, welcome back, guys. We're just gonna jump straight into this, our different programming methods. We've looked previously at the different types of movements that there are, into the generation of programmings, how we're currently in our 5th generation right now with all of our AI-driven programming and data. So let's look now into those 4 methods a little bit more deeply. So we're going to revisit manual programming. That involves, like walkthrough, our teaching pendant, and our computer programming. So again, each of these kind of represent, they have like trade-offs between each other. Some are more simple, some are more sophisticated, some are a little bit just easier to learn how to use. This chart just gives you a quick rundown. So if you want to pause the video, read through the chart, please do so. Each of these, though, is a step towards our modern system. So as we modernize, it requires less human effort manipulation-wise. That's gonna decrease, but that increases the amount of advanced tools that we need. So that causes for a scale increase. So let's go through each method and how it's applied in the industry. And we can actually look through that. Best way would be through like a chart. So if we have here, we'll just make a simple XY chart. Our starting point, we'll have it be ease of use. And then as we're going more across, it's going to be how complex it is. And then on this bottom part will be human effort. Up into our automation that we're in right now. So at the very, very bottom, we have our manual programming. This is our baseline. And then over the years, we entered into our next generation, which our next generation gets us into our teaching pendant. So at this point, with the teaching pendant, we've improved usability. The operator is now using a handheld pendant to basically jog or just record every single position. But it still requires manual controls. So we still have to do manual movements through the controller and run it on a coordinate-based system to know where it needs to go. After we've gone through the teaching pendant, we enter then into our walk-through, lead-through programming. So when we're here at this point, the robots can record its path as the operator is physically moving it. So a little bit less manual coding because it's just constantly recording now. So as you're moving, it is just constantly recording. You don't need to move it to a position, press record, move it to another position, save the position. It's eliminating that element of it. And then we get into our current one right now, which takes a very large jump into our automation and complexity on our X and Y chart. So here we are at our computer programming. So this is, offline simulation, code generation, all of our CAD-based planning. It's a very powerful system that we have, but again, it requires a lot more advanced software, a lot more skills from the user, it needs a lot more power to get through. And you can kind of see here, again, we're starting here at the very, very bottom. Everything's manually programmed. You have to go through every single robot. You get up into our teaching pendant again, which is still used. We still use this quite a bit. We use this with a combination of computer-based programming now today. And then you have your walk and lead through, which is a little bit of a mixture between these two systems. And then we make this very large jump up into our computer-based system that we're using now. And that's what all of our AI systems are using now. So let's look into our manual programming a bit. So our manual programming, it's going to be the most basic form of direct manipulation. You're moving every robot's joints or inputs. It requires no software, but it is slow. It's unsafe for any large systems. These robots are all open loop systems. They execute motions without any feedback, so they have no idea what they're doing. They'll just keep moving. Then you have your focus on the teaching pendant. So again, teaching pendants are still widely used in factories today. Operators can move the robot via like a handheld controller, like this one. It will store each position and adjust and you can adjust its parameters on like speed or delay. Just a couple of different things you can do with that there. And then some pendants now can support like simple logic commands, so like even loops or conditional statements, making them pretty much semi-programmable. So you can say like, hey, if this happens, enter into this coordinate programming. So change how you're moving now. So it's kind of that perfect balance between safety and flexibility, but it still does require you to stop production during its initial setup, or if you're trying to get it set up into a currently running, like a current environment, you need to shut down everything. And then walkthrough programming. Walkthrough programming combines all of our physical guidance and digital recording. So the operator is manually guiding the robot arm through the desired motion. The robot's sensors record joint angles all in real time. The motion path becomes a stored program. It is really ideal for tasks like welding, polishing, painting, where smooth, like human-like motions are important. Its main drawback is safety, because the operator still has to physically be in the environment of the robot. So it has to enter the robot's work envelope. So that's still a concern, but it is a little bit more accurate because now you have all the points. It's all recorded, so it will move more human-like. Now you're probably wondering, well, what's the difference between manual programming, a teaching pendant, and a walkthrough? Well, manual programming, think of it's you're telling the robot what to do by numbers. It's very technical. There's no direct or like physical movements. You have to tell everything to be done by numbers. Teaching pendant. Well, a teaching pendant, you're driving the robot now to each point using buttons, or like a joystick, knob controls. Still manual, but it is more visual, so you can see kind of what's happening. And then you have walkthrough, where you are physically guiding the robot. Think of it like you're teaching it how to dance. The robot can feel and learn its motions. Then we enter into our computer programming. Computer-based programming is now the industry standard. Engineers will write code in robot languages using offline softwares. They can test it virtually through simulations, and then they just have to just download it into the controller, and it's sent through the server cloud. And then every single robot has that controller now. It has all the code. It does, though, have its limitations, where not so much limitations, but it is a very complex logic to use. It is nice that it has sensor integration. You can do multiple robot coordinations while keeping the robot production running. Again, though, the downside is that you do have to be skilled in programming. You have to have an understanding how all these tools are used. Training is essential for every single technician. You have to be trained, know how to use the software, how to program, and how all of that's going to translate into the real world. So here are some basic robot programming languages. Not basic, but these are, again, the pretty common ones that are used. We have our vendor specific ones. So if you have any of these robotic arms, you have to use their system. And then we have our general ones that we see here today: Python, C++, MATLAB. And then we have more of our graphic ones, which are Sketch, where we're blocky, LabVIEW, so it's kind of like a drag and drop situation. So with everything in robotics, there is always a hierarchy. Programming is also organized in that hierarchy. So from a low-level motion, we start from our low level, which is motion control, go all the way up to our high level, which is our decision making. At the lowest level, we control actuators, directly through numerical commands. At the mid-level, we use motions, pretty much just language-based. Instead of commands, we're saying move to position A. You don't have to say move to position X equals 2.5, Y equals. You don't have to give it a specific number. You just have that data point saved as B. And then at the highest level, you give task-based instructions that are just pick up an object. Again, how it does that is up to the robot. You just give it its command, pick up an object. So each layer, it's going to be building upon each other, and we've talked a little bit about this beforehand. Each one is an organized system. They're all working together to make this whole entire hierarchy system work correctly. So we get into the task level programming of that, we don't tell the robot how to move, we simply describe what to achieve. So for example, assemble this part or inspect this object. The robot's internal planner figures out all the sequence of motions, and this is all AI driven. So you have frameworks like ROS, which we've talked about is the robot operating system. The robot understands a task, but how it gets to those coordinates, that is up to it to do. So for example, I'm going to give the command stack a box. So our goal here is to stack a box. Well, the robot knows its goal, but it doesn't know how to get to that. So it's going to have to come up with a path all by itself. So the robot on its end looks for the box, it needs to decide how to move to the box, needs to decide how to grab the box, then it needs to decide where to move the box. So all that we did was give it its goal. This is what you need to do. And then now the robot has to think about all of these decisions and how to do that, how to execute that. So it kind of comes back into our task. The robot needs a plan, and then it needs to execute that. So on a task level just pretty much equals it focuses on what it focuses on what it needs to do. And then it will start to think of initially, okay, how do I get to that point? So that goes into our voice recognition. Voice recognition is starting to become a little bit more popular in robotics. It does have quite a few errors though right now, just given that it, in a noisy environment, it's a little bit harder to use. It is one of the newest forms of human-robot interaction. So pretty much you have to give the robot a speech system. It has to be able to convert sound waves into digital data and process it to recognize commands. It has to map all of those commands into an internal action of what it needs to do. So you can say hello, like if you have like with your phone, you say like, hey Siri, or you can say like, hey Google, or like, hey Alexa. Like you have different ways that you give a command. It takes your command, your sound waves, and then converts it over into an executable command. And again, that can apply to, like we're saying, pick up the red box. Well, now the robot knows more specifics. It doesn't know it needs to pick up a box. It needs to pick up specifically that red box. So it's just able to take in a little bit more data. And then voice communication is actually the robot can talk back to you. Let's say there is an error. Well, if you just have like a red alert going off, you may not know what is the error for. There can be so many error codes that you have for a robot. If you have a robot that can talk back to you and say, hey, my gripper isn't gripping as hard, I'm starting to slip, like the objects are slipping. If it can tell you that, well, now you know where to put your focus in. It's less downtime. You know where you need to work at. It is a lot quicker and safer because instead of having to tear apart a whole entire robot trying to figure out piece by piece what's going on, you know specifically where to look now. So I haven't personally seen voice communication used that much, besides for like a fun kind of base where you're just kind of messing around and you're just like wanting to see how it works. But it is something that is possible depending on your situation. Again, you need to make sure the environment isn't too loud that you can't even hear the robot communicate with you. And then we have our robotic simulations, which we've been talking about for a bit. This is allowing engineers to program in a virtual environment before touching real hardware. It can check motion paths and make sure your environment's safe. You have all of your safety features in play. You can calculate physics. You can calculate reachability. You can estimate how long cycle times take. Simulations give you so much data before having to throw it into the real world and potentially make a very dangerous mistake, or potentially have your production, like your revenue, go down because of something that could have been easily preventable if you ran it through a simulation. And that pretty much is going to wrap up this lecture. Again, we'll have a couple videos. We'll discuss everything in class, but hopefully that kind of gives you a good idea of the different type of programming languages that we use in the industry today, kind of where we're going. Right now we're going to be in our 5th generation for a while because it's AI driven. AI is constantly changing, weekly, daily, to be honest. So we're going to be in our 5th generation for quite a while. I'm not sure what the next big thing will be after AI, but we'll see. Awesome. I'll see you guys in class.